Hi, this is Mrs. Robel. This is part 4 of Electrons and Atoms. So far we've discussed what is light, how do we describe it. When we're looking at electrons, we need to look at the energy levels. What's the frequency, what's the wavelength. We've looked at the Balmer, Lyman, and Paschen series in hydrogen. Now we're going to look at the electron. How does the modern atomic theory treat it? We're sort of looking for the address or the location of the electron because that's going to be important for us when we look at things like chemical bonding. So Schrodinger was a very wise, mathematically inclined physicist. And what he did is he described the electron as dualistic. And what he meant by that term is, gee, this is a familiar theme. Sometimes the electron can be seen as a particle. So remember how we talked about light acting as a particle, as a photon? Well, guess what? We're treating the electron in a similar fashion. Also, Schrodinger treated the electron as a wave. And the wave, we can actually tie that into de Broglie. I don't know if you remember, you saw it with the wave functions or the movement of the electron in a wave vibration. So Schrodinger, he saw the electron essentially as a particle or a wave. So what he did is mathematically, he took that electron and he described it as a three-dimensional standing wave. We're getting into some really heavy-duty math here. This is something that a lot of physicists struggle with to try to describe to people in non-math terms, and it's very challenging to do that. I'm going to show you some pictures of one-dimensional standing wave and a two-dimensional standing wave. If you're a musician who plays a stringed instrument, you may have seen these vibrations when you pluck a string. Okay, so here are some examples of standing waves, and these pretty much come into play with sound. So when you have a vibration with a string, you could have essentially half of a wavelength. So this is for n equals 1. Notice that when we change the energy level, we're increasing the amount of energy here. We have essentially a set of 2 half wavelengths. For 3 energy level, we essentially have 3 half wavelengths. Now, notice that this is associated with a guitar string. So if you were to pluck it with the right frequency, you would essentially get these type of standing waves. Now, with an orbiting electron, it's a little bit different here, but we're almost incorporating the same thing. So the bottom left-hand side almost is similar to the top right-hand side. The only difference is we're talking about a circle as opposed to a straight line. Notice with n equals 5 wavelength, we're increasing the amount of half wavelengths that we have within that circle. Notice that n equals a whole number is not allowed, and that'll make more sense when we talk about things like quantum numbers. Okay, here we go. So like I said, Schrodinger's treatment of the electron is very challenging. It's essentially pure math, and I've done some of the math. It can give you a headache. So we're talking about pure math, and you need calculus to describe this. So he's actually creating an address for the structure of the atom. This address has what we call quantum numbers, and these quantum numbers are included in the equation that Schrodinger uses to describe where the electron is. Now, this is something that is very difficult to understand sometimes. This actually gives you a probability that the electron is in that location. What this means is we don't know at that instant the exact location. We know there's a good chance that electron is going to be found in that location. So it's a very nebulous type of treatment with the location of the electron, but the math works. Okay, so quantum numbers are going to be your friend with this part of the chapter. What does this mean? Well, that means for the address, when we are describing where the electron is, we first have to look at the n number, which is the energy level. So remember how we were talking about the Lyman, the Paschen, and the Balmer series? They all had energy levels that are associated with each type of series, and we're using the same energy levels for that to describe. What this means is the higher the energy level, the more distance the electron is from the nucleus. Now, this next number is what we call the sublevel. So the first part of the address is called the quantum number. The second part is the sublevel. So this actually tells us the type of vibration. I always think of it as like an electron cloud, and it'll make more sense once I show you some of those shapes. But we're looking at the shape of the sublevel. So each sublevel actually has a specific shape associated with it. Okay, so notice that if we have one energy level, we only have one sublevel. So that diagram or that model that I showed you for the Schrodinger had one slot. Here we have energy level 2. Notice that there's two slots. There's a 2s and a 2p. For energy level 3, there are 3 slots. So there are 3 types of sublevels. And notice for energy level 4, there are 4 slots. For energy level 5, there are 5 slots. So if you had to guess for energy level 6, how many slots will there be? Correct, there'll be 6. Okay, so after we've looked at the first 2 quantum numbers, we need to look at a third type of quantum number, and this is called the magnetic quantum number. What it does is it describes the orientation of the sublevel. So we're breaking down more information. We know what the sublevel is now. The additional piece is where is that electron located within that sublevel. Now, notice that if there are n squared orbitals, there's that per energy level. So notice that S has 1 orbital, P has 3 orbitals, D has 5, F has 7, G has 9. So these sublevels have that many orbitals within that sublevel. And it'll make more sense in a little bit. The last quantum number is called the spin quantum number. And what that means is essentially is the spin up or down. So notice if it's positive, it's located, if you want to look at the planet as an example, notice that it's pointing down if it's positive, it's pointing up if it's negative. Okay, so this ties in with the vibrations that you saw when I was showing you some of the models, more specifically the Schrodinger model. So notice the Schrodinger model, when we're looking at an s orbital, we're essentially looking at a sphere. So if you want to think of it this way, whenever you see the s orbital, we're talking about a sphere. You can only fit 2 electrons in this sphere. So no matter what the energy level is, it could be n equals 1 all the way up to n equals 7, for instance. Each s orbital will only contain 2 electrons. Now, for the p orbitals, this is where it gets a little more complicated. We have a total of 6 electrons, and there are 3 main orbitals. So notice that there's a px a py, and a pz. Now, all this means is that the p orbital is on the x-axis or the y-axis or the z-axis. And when you put them all together, it sort of looks like a flower. In each p orbital, each subtype, you can fit 2 total electrons. Okay, with the d electrons, once again, we're building complexity here. We can have a total of 10 electrons. Now the good news is I will not ask you to draw these type of orbitals, but just to let you know, we're talking about the orbitals are along the xz axis, the yz axis, the xy, the x squared minus, that should be a y squared, that's a typo, and then z squared. So please notice there's 5 different possible locations, and each subset of the suborbital can contain 2 electrons. So even though there's 4 lobes, you can only put 2 electrons in those 4 lobes. Okay, yes, we can get even more complex, which is amazing. Nature has a very interesting way of making itself very challenging to understand. So here we have 14 electrons. So this is the f orbitals, and yes, it gets even more ridiculous with the type of drawings. So even though there's, let's see, 1, 2, 3, 4, 5, 6, 7, 8 lobes, you can only fit 2 electrons in those lobes. But notice there's 1, 2, 3, 4, 5, 6, 7 different types or subsets of the f orbital. And these are essentially the mathematical equations that you can get from the location. And this is probability of the electron. So we don't know for sure where exactly the electron is, but we have a good idea that it's probably within that region.